the invitation. It's a real pleasure to speak at CVPR and for such a great audience. Thank you very much. So my name is Matthias Fey. I'm about to finish my PhD next week and currently also employed as a founding engineer at Kumo AI, who build GNNs for industrial applications. And today my talk will be more about the practical aspects of graph neural networks, in particular, how we can efficiently implement them in practice and apply them for different tasks and applications. So I also have a brief introduction into graph neural network, but most of that was already covered in the previous talk, so we'll quickly go over that. And so graph neural networks update node representations by repeatedly transforming and aggregating representations of their direct neighbors. And so we can think of that blueprint of that function f, which is parameterized, and it takes in some central node representation in layer L of a node V. And it also takes in this multi-set of features of the direct neighbors of that node. And what we get as an output here is a new representation of that certain node for the next layer. And so this blueprint is then often decomposed or referred to as a message pattern scheme in the sense that it has three major building blocks. One is that we first send a message per edge or per neighbor to the given central node. And that message can be written as anything you want, and it often is referred to as taking like the input of the source node features, but also like the destination node features or optional edge types and so on. And so that gives us a new vector or new representation back. We can use this representation now to aggregate these messages across all neighbors that point to the same destination node. And so this aggregate function is usually referred to as a permutation invariant or a permutation equivariant function. It isn't required to do so, but it is often done, and most GNN operators just simply use a sum or a mean or max aggregation. After that, we get a back-to-back that represents the direct neighborhood of each central node. And we can use this representation to update the central node representation using a different or another function, which we often call update. And so that update is often implemented as a simple skip connection or similar. And so importantly, all these functions are trainable and differentiable. So we can use them in a deep neural network and use them as building blocks that can we train jointly and end-to-end together. And importantly, all these functions are shared, like have shared parameters across nodes and graphs. And what that means is that we can easily apply them to unseen graphs and unseen nodes as well. And so if we use these layers, these message passing layers, in a deep neural network architecture, then they can be also stacked and enhanced by nonlinearities. And what that means is that after L layers, we've exactly aggregated the L hop neighborhood representation around each node. So if you have like L layers, then the representation that each node has corresponds to a view of the local subgraph around that node. In general, this message passing scheme is super flexible and nearly everything can be implemented with that. In particular, besides all these standard GNN formulations, you can get really fancy here. For example, you can use anisotropic transformation, which means that the message not only depends on the source node features, but it also depends on the destination node features. And in that way, you learn different transformations for each neighbor individually. You can also apply your message passing scheme across different edge types. And that means that you potentially can learn a different transformation for a neighbor depending on which edge type it has a connection to the central node. Importantly, it can also incorporate edge features. There exist many different ways how to do that. One of the most famous is that we can condition some kernel function that takes in these edge features and basically learns a transformation such that we can transform the given neighbor. And so graph neural networks using this message passing scheme are super flexible, but they're also generalizing all these concepts that we know from different domains. So for CNNs, these learn discrete local patterns that are universally applicable, and the GNN does actually do the same. So it aggregates the local neighborhood around each node or each pixel and aggregates it together. And all of these patterns that we learn, these are universally applicable over all nodes in our graph. But instead of like limiting ourselves to discrete kernels or a fixed neighborhood size, we can now incorporate varying neighborhood sizes and can actually learn continuous kernels that are used to transform a given neighbor. The same holds true for the transformer, which we've known from our earlier talk. And so transformers build features of each word by attending to all other words in that sequence. And that is similar to the concept of message passing that uses attention, but within a fully connected graph. And so GNNs both generalizes CNNs and transformers, and actually many, many more architectures. What in my mind is the important takeaway here is that GNNs actually define a new paradigm of how we define neural networks. In particular, I don't see them as much dependent on the operating on graph structured data, but more of how we define neural network in the sense that the computation graph of our neural network is no longer fixed or part of our pipeline, but it's actually part of the input. And so we can just change the input and our deep neural network behaves differently. Importantly, due to the generality of message passing graph neural networks, there exists like a large amount of applications. One of the most common one in graph machine learning is, for example, recommendation in social networks, where we want to recommend users products or new friends or whatever. We also see them applied in chemistry, where we learn on molecular graphs and want to predict certain molecular properties. And we also see them used in knowledge graphs, where we want to infer missing links or missing knowledge. For computer vision, we see them also used in 3D processing, where we learn like local patterns of geometry, for example, given on mesh-like data or given in the form of point clouds and so on. We also see them used in graph matching, in particular for the task of key point matching, where we're given a set of key points per images, and the task is now to find correspondences between key points in different images. One major big topic is the field of scene graphs and motion capturing. For example, scene graphs are used or describe objects in a scene, and these objects can be given by a bounding box detector or object detector. And now we can use we can now use GNNs to infer or relate all these objects together and to manifest our understanding of that scene. And so for motion capturing, the same was true, where we represent our scene into human body parts or joints. And now we can use GNNs to operate on this skeleton data and to process this data. One of the most rising fields where GNNs are used is a view of our structured world model, where we now no longer see our world as an unstructured place that gets fixed into a single latent vector, but we actually first learn about objects in our world and then can use GNNs to relate these objects and to make better predictions afterwards. And so there exists a lot of a lot of applications, a lot of GNN flavors and so on. And so this talk will mostly focus on how we can implement them efficiently. And one solution towards that is the Pytorch geometric library, which I developed during my PhD. And that is a Pytorch library to enable basically deep learning on graphs, point clouds, and manifolds. So this is basically the missing piece of Pytorch to enable graph neural networks. And so PyG simplifies implementing and working with graph neural networks. So it should be super easy to write your new GNN layer, to write new GNN models that fit to a specific domain, to a specific task. It should also bundle state-of-the-art GNN architectures and training procedures, so you don't have to rewrite everything from scratch, and you can also directly compare yourselves to state-of-the-art and related research. Most importantly, we also try to do that as fast as possible. So we always aim for high GPU throughput on highly sparse data of varying size. And in particular, we do that by providing some extension libraries that are especially designed to work on sparse and graph-specific data. Lately, we are also trying to make PyG both suited for academia and industry. For academia, that means that PyG needs to stay flexible in the sense that research should not be limited by its scope. And for industry, it means that we also wanted to have to be comprehensive and easy to use, such that new advances in graph representation learning gets immediately applied to industry applications as well. And so for myself, I like to frame PyG as Pytorch on the rocks. And what that means is shown in the given figure. And that means on the left side, we have a CNN that is a two-layer CNN. And it follows like the classic Pytorch principles of defining defining operators in the init of a class, of a module, and then defining the computation graph as part of the forward method. And so here we define two convolution operators on the left, and in the forward, we just enhance it by a nonlinearity. On the right, this is actually how a GNN module looks in PyG. And so it nearly looks the same. So we again have our constructor, but instead of initializing convolution operators that expect grid-like data, we now have operators that expect any graph structure as input. And so here we specify again the input and output channels of our GNN. And in the forward, there's this crucial missing piece where we now take in the input, the node feature matrix, but we also define this edge index representation that basically says how our node features or how our nodes are connected in that graph. And that edge index is typically just a long tensor that stores like pairs of node indices that represent source and destination nodes. With that, the execution looks exactly the same, but we also always take this input of this tuple of node feature matrix and graph structure as input. Importantly, we now take a look at how message passing is implemented in PyG. And in PyG, every graph that we represent is given in a sparse format. And that means that we only store the non-zero elements of our adjacency matrix. And so our graph is given as a node feature matrix H0, which basically represents the initial state of the node features or the features of every node stacked into a big matrix. And then we have this edge index representation I, which is given in the form of a 2 times number of edges matrix. And on the right, you can see a simple example of how that may look like. So we have our source node in the first column, and then we have our destination node indices in the second column. Importantly, we transpose this edge index representation here to have like contiguous access to a source and destination node indices. And so optionally, we also allow edge features and many, many more attributes depending on the GNN layer and architecture. And so to recap, we want to implement this message passing scheme, which is decomposed into these 3 parts, where this aggregation operator is usually a permutation invariant operator, such as sum, mean, or max. And so in order to implement that, we make use of a really flexible implementation in the form of a parallelizable gather and scatter scheme. And that is all condensed into a general message passing interface. And so what that means is that we first gather all the information, all the feature vectors into an edge parallel space where we can compute the messages in parallel. And so for each message or each edge we want to compute a message for, we actually materialize all the different representations. And that means that we can now apply any message we want in the batch-wise mode or in the parallelized edge level representation mode. After that, we have a message for each edge available, and now we can scatter or aggregate all these messages together depending on the destination node index. And here we make use of scatter aggregations. That means that we utilize atomic operations which highly parallelize across different destination nodes and features. And so this scheme is parallelizable in all these three parts. And finally, we are back in node level space. And that means that we can now combine or update our node level representation by the previous representation and the aggregate of the scatter output. So how does it look like in code? So imagine that you're given this edge convolution operator on the top right, which just computes a new node representation by taking the max over all neighbors, where the message is computed using an MLP on top of the concatenated input of source and destination node features. And here xi refers to the representation we want to compute the embedding for, and xj refers to a neighbor representation. And so there exist 4 steps to define a new message passing layer. The first one is that we have to inherit from message passing. And so we can just write our edgeconf by inheriting from message passing interface. Next, we need to select an aggregation scheme to use. So you can also define your own aggregation scheme, but most people, most GNN layers just make use of a predefined set of aggregations. And so here we just input into the base constructor that we want to apply a max aggregation scheme. In the forward pass or in the forward computation, we just need to say at some point that we want to start propagating messages. And so we do that by calling the self.propagate call, which is conditioned on this edge index representation. And after that, everything is passed to that call that is later needed to construct messages. And here we just need the node feature matrix to construct our messages. Internally, this self.propagate call will call the message function. And that message function has the capability of inferring all the input arguments from this self.propagate call. And so we can just say that we request the source node representation and the destination node representation by calling this _j and _i in the input arguments. And so this will automatically convert the node feature matrix AX to an edge level representation, depending on whether you're interested in the source or the destination node. Using these input arguments, we can then compute the message fully in parallel. So we could just concatenate them together to form some kind of edge feature and apply our MLP on top of that. And that is all we need to do to implement this simple edgeconf layer. In general, these message and update functions are really easy to write and compute since they only operate on individual elements. So we've seen earlier that we can just apply a simple MLP in the batch-wise mode for all these different edge representations. And the real challenge really lies in providing efficient aggregations. And I quickly want to recap the different modes of the different strategies of performing aggregations in GNNs. One is the scheme that we've seen earlier, which is called like the gather and scatter scheme, where we start with a node feature matrix, and then we have this intermediate edge level representation that computes all these messages in parallel. And after that, it aggregates all these messages together to again form a new node feature matrix. And so we've seen this scheme is very flexible, and it is very fast for sparse graphs. Importantly, it will struggle on more denser graphs, in particular because it is very memory inefficient or memory bound, in the sense that we explicitly need to materialize this edge level representation, which can get pretty big if you're dealing with dense graphs. So one alternative to that is the sparse matrix multiplication approach. We just take this edge index representation and really represent that as a sparse matrix. And then you simply take the matmul of this adjacency matrix with a node feature matrix. And the output will be a new node feature matrix that just aggregates from all the different neighbors. Importantly, this scheme is less flexible because it is only applicable to a certain set of operators. In particular, as a general rule of thumb, you can only use this scheme on GNN layers that only transform the neighbors with the same transformation matrix. And so it does not really can incorporate edge features, and it does not really can incorporate central node representations. And so it is considered less flexible, but whenever there is a GNN layer that can be framed as sparse matrix multiplication, there's really no reason to not use it or leverage that fact. And so if we can represent our GNN layer as such, it is very fast and very memory efficient to just perform a sparse matrix multiplication. Another approach I want to highlight is the degree bucketing approach. It is pretty hard to visualize. I will try to explain it. As far as I know, it is pretty common in computer vision, and it's also pretty popular through the GGL library. And here the idea is that we, again, have an edge level representation, but we reshape that into a representation of the form num neighbors times the max degree times the number of features. And so the idea here is that we have a dense representation of our edges where we can use dense operations to perform the aggregation. And that is like we perform the aggregation in the second dimension. Importantly, you can do this for each degree possible. So you would have a list of representations where only the number of degrees, the second dimension changes. You can also prevent to have too many different representations by using padding and so on. In the best case, when all nodes in your graph have the same amount of neighbors, you can have just this big edge level representation of shaped num nodes times the degree times the number of features. And the cool thing about this approach is that it actually can implement any aggregation. And so you can basically use any Pytorch dense function available to perform the aggregation, such as LSTMs, GRUs, and so on. The downside is that this comes with a trade-off. So it is very memory and inefficient. And in the worst case, it is far more memory inefficient than the gather and scatter approach. If we use a higher number of degrees or a higher number of buckets in which we group our representations using padding, then this will amount to a sequential iteration where we need to iterate over all these representations and perform the aggregation sequentially. And so there's a trade-off, but if your aggregation cannot fit into the scatter or the sparse matrix multiplication approach, this is usually a good alternative. The last aggregation scheme I want to talk about is what I call the individual kernel, which just means that we have a specific implementation or a highly optimized implementation for a given GNN layer. And that is given through CUDA or low-level code. And that means that it's not flexible at all, but you cannot really get faster than that or more memory efficient. On the downside, it is to note that it's practically more applicable for inference cases, since you will lose out on the ability to reuse intermediate tensors during the backward call. So you would have to recompute them to compute the gradients for the given parameters. One thing I also want to talk about is that over the last few years, there had a lot of research being put into finding better aggregations. And what I mean by that is that we've seen aggregations that are learnable. We've seen aggregations that are attention-based in all kinds of forms. And we've also seen the usage of multiple aggregations where we combine them and concatenate the results together and so on. And so previously, PyG did not really have that concept of an aggregation as a first-class citizen, but we're actually about to change that with the usage of our new aggregation package. And the idea here is that we expose any aggregation as a simple base class, which the user can customize and fully extend. And so the idea here is that instead of providing this aggregator some call, you can actually define any aggregation you like. You can also combine them together, uses this multi-aggregation function, which just takes as input a list of different aggregators. You can combine some aggregation with attentional aggregation or even LSTM aggregation. Importantly, each aggregation will pick up the best format that is needed to compute its representation. And so for sum and attentional aggregation, we can still make use of this fast and flexible scatter operation of sparse matrix multiplication, while for others, such as LSTM aggregation, we default back to this degree bucketing approach. While it is not yet fully integrated, optimization of the scheme is also possible in the form of fusion, where we can say we want to fuse the aggregation of different, where we want to fuse the multiple aggregations into a single execution. And that has the advantage that we can reuse the vectors, the input vectors across the different outputs and do not need to access them every time we compute a new aggregation. PyG also supports mini batching on many small graphs, and I just want to highlight that here because it's really famous and pretty important topic when you start building GNNs. And the general procedure here is that you represent your set of graphs as one giant supergraph. And so that supergraph just has a set of isolated subgraphs that denote your input examples. And you can actually do that by just stacking your adjacency matrix in a diagonal form and concatenating your node features in the node dimension. Importantly, this will not require any GNN modifications because, as you can see, this supergraph or message passing on the supergraph will not exchange messages between examples, between nodes in different examples, because they do not share any edges. And also, it does not have any memory or computation overhead because all our adjacency matrices are implemented as a sparse matrix or in a sparse form, and so we only store the non-zero elements. And in addition, it supports examples of varying size. And so what that means is that you can directly load in the data set given in PyG. You instantiate that data set and put it into that PyG data loader, and PyG will automatically take care of providing this correct mini batching approach. One thing I want to highlight is that PyG merges these batch and node dimension into a single dimension. And in my understanding, since I've worked so long with that, it's super intuitive. I understand that people have problems with that, and there's an alternative approach emerging that is called, or that is referred to as nested or ragged tensors. And the idea here is that we still have this notion of exposing the batch dimension, but the actual dimensions can change in size. And so what that means is that our tensor is still represented or exposed to us as a three-dimensional tensor, but each element in this tensor or in this matrix can have varying size. And so if you look at the Pytorch package, it actually has support for nested tensors in the latest release, and you can just do this or create this nested tensors by just passing in a list of different individual matrices that potentially may have different sizes. I want to highlight that this sits at the heart of the TensorFlow GNN library. So if that sounds interesting to you, you should have a look at that package as well. And the Pytorch API is for nested tensors in prototype stage. and we've seen to integrate that into PyG as well anytime soon. I quickly want to give a short example of how PyG workflow looks in practice on a simple toy example. So consider that you want to perform point cloud classification, and you want to do that on a toy data set, which is called geometric shapes. PyG provides that data set, and that data set contains 40 examples of different shapes, which you simply want to classify into a given category. And so you can just instantiate that data set in PyG, specify a root directory, and PyG will take care of downloading and processing that data set. And if you want to access given graph or given example of the data set, you can simply do so by index notation. And if you print that out, it gives a nice overview what is actually contained in that graph, in that data example. So here we have like a position matrix, which is of shape number of nodes times 3. Like it will have a 3-dimensional coordinate for each node or each point. It also has a phase matrix of shape 3 times 30, which means these are just the indices of defining triangles in our mesh. And then we have this Y attribute, which is denotes the category of our data object. You can use point cloud sampling, or you can use the concept of transformations in PyG to simply convert your data to a new representation. So transformations take data in and output new data. And so the sample point transform will simply sample points from mesh phase area uniformly and give you a point cloud back. And so after printing that out, you will actually see you have a position matrix that is now a shape of 256 times 3 instead of the original mesh object. You can even compose transformation using the compose transform class, and where you can say we first want to sample points, and after that we want to create a graph out of that just connects the k nearest neighbor of each point. And so when you do that, you will see that you get an additional attribute inside your data object, which is called edge index, and that has the shape of 2 times the number of nodes times the number of neighbors we requested for each node. Given your data, you can now easily instantiate your GNN model and apply it for training. So given our edge conf representation from earlier, we can just instantiate 2 operators, and we can also instantiate a final classifier that maps our graph level representation to one of the certain classes. And in the forward call, we just stack our convolution operators, and we apply a global max pooling that is conditioned on the node representations after the 2-hop layer aggregation, and this additional batch vector which denotes to which example each node belongs to. And on top of that, we apply this final linear transformation, this classifier. And then training this looks exactly the same as in regular Pytorch. So you instantiate your model, you instantiate an optimizer that takes in these parameters as input. You define your data loader to get mini batches back and apply the training in mini batch mode. And then you simply iterate over your data. You clear the gradients of your optimizer. You compute the forward pass of your model. You compute the loss based on the predictions of the model and the ground truth labels. You apply your backward propagation, which gives you gradients for your parameters, and then apply the final step call, which updates the parameters according to the gradients. I quickly want to go over some additional highlights before running out of time. Since this is just a shallow overview of the high-level concepts of PyG, there's much more to discover. One additional highlight is heterogeneous graphs. And so we have full support for heterogeneous graphs, which have different node and edge types. And there's also the ability to convert standard GNN models into their heterogeneous counterparts, which is very convenient to use. We give a lot of focus on scalability, and so we try to make a GNN model scale seamlessly to large graphs with more than 8 different samplers available. And the general procedure here is that you instead of having a data loader, you now have a loader that assembles subgraphs from your graph. And so it just takes in a single data object and gets you back a subgraph of that. We also tried to integrate Torch script in the sense that you can easily convert your Python module into a standalone representation. We've worked hard to bring in Pytorch Lightning support in the sense that it easily gives you multi-GPU support. You can choose different accelerator types and simply call trainer.fit afterwards. And we worked hard to bring in explainability in GNN predictions across a variety of GNN models, data sets, and tasks, and that all out of the box using the Captain library. So overall, PyG has been a great success so far. I really appreciate all the support and thanks for all your contribution and issues and so on. It helps the library tremendously. Importantly, PyG already has its own ecosystem on its own, so that's pretty cool to see. So there exists extension to perform temporal learning. There exist higher level libraries to make it easier to use. There exists library for distributed training and so on. We've made great effort in giving users a good introduction into GNNs, and we provide over 80 examples across different tasks, and also recently published some GraphML tutorials on Medium, which is fully realized with PyG and corresponding notebooks. And with that, I'd like to conclude my talk and happy to take any questions. Thank you.